por venir a Latinar, la conferencia latinoamericana sobre el uso de R en investigación y desarrollo. Estamos felices de finalmente hacerlo en Montevideo. Les contamos cómo fue, porque para muchos de ustedes es la primera vez que vienen a Latinar, ¿sí? Arrancamos en el 2018 en Buenos Aires. A muchos de ustedes los conocimos ahí, los vimos por primera vez y ahí arrancó esta aventura de Latinar. ¿Sí? Ahí tenemos algunos recuerdos de eso, de ese momento. Después fuimos a Santiago en 2019, que también fue un gran evento. Y después, ¿qué es lo que pasó? Todos sabemos la historia trágica, ¿eh? ¿Sí? Y ahí, ¿qué pasó? 2020, pandemia, y el plan era hacerlo en Montevideo y lo tuvimos que suspender por la pandemia. Seguimos haciéndolo, pero virtual, ¿sí? ¿Se acuerdan que nos estuvimos viendo por un tiempo? Virtualmente. También pasó que en el 2021 dijimos, se va a terminar la pandemia y vamos finalmente a tenerlo en Montevideo, y no fue posible y llorábamos, porque es importante el emoji, ¿está? Pero finalmente, ¿no? Y ahí lo hicimos en línea, igual ya estábamos acostumbrados a esa realidad. 2022 se había ido de la pandemia, pero bueno, no había voluntad, ¿se ve? Estas chiquilinas no me querían trabajar y hicieron virtual. No, es una cosa tremenda eso. Y seguimos llorando. Pero finalmente, después hicimos en línea y ¿a dónde estamos? 2023 y estamos finalmente en Montevideo haciendo nuestro Latinar. Fue un largo camino, pero llegamos a casa. Y bueno, y eso es todo de la historia. Y nos presentamos, porque muchos de ustedes capaz que no nos conocen. Acá tenemos a Dianne Bellini, que vino manejando desde La Pampa, un largo camino, tan cerca pero tan lejos. Tenemos arriba a Quiroga, que no vino manejando, pero vino desde Santiago. De Valparaíso caminando se vino, no se vino caminando. Y yo, que me llamo Natalia da Silva, que estoy acá, no caminé mucho, y bueno, y ahora pasa.
Bueno, como siempre, ninguna de estos eventos y de estas iniciativas que tenemos en la comunidad de R sería posible sin todas las personas que trabajan atrás. Nos toca a nosotras tres estar acá, pero hay un montón de gente siempre trabajando y haciendo que esto pase, y además de forma voluntaria. Así que aquí están, le vamos a dar las gracias, un aplauso, y si quieren, si están acá, se pueden parar, la gente del comité organizador, así los conocen. Ignacio, Mauro, Andrea, Beatriz, Juan Pablo, el Tucu, Macarena, Jessica, María, Roberto, Luis, Pao, Elio, Patricia, Fabricio, Estefan y Bruna. Después también queremos agradecer a nuestro comité científico, quienes leen los resúmenes y nos dan un buen feedback para que después podamos hacer hermosas charlas que todos disfrutamos acá. Sara, Marcela, Ignacio, Virginia, Zulema, Naim, Elio, Jocelyn, Marina, Cristina, Paola, Juan Cruz, Andrés, Felipe, Alejandro, Denise, María, Adriana, Carolina, Juan José, Jennifer, Juan Marcelo, Leonardo, Ricardo, Estefany, Francisca, Felipe, Vilma, Germán, Gabriela, Alejandra, Inés, Luis. Muchísimas gracias a todos ellos. Muchas gracias a nuestros sponsors aquí, a la facultad, por tenernos, por prestarnos esta sede tan hermosa, y a toda la gente que ha estado colaborando para que estemos hoy aquí. Muchas gracias al Arconsortium, a Apsilon, Cicada, y a las comunidades amigas ArOpenSci y ArLadies. Y muchísimas gracias al equipo local de la facultad, Laura, Victoria González, al equipo de registro, de electrotecnia, de comunicaciones, de vigilancia y al decanato. Gracias totales por hacer esto una realidad.
Ya, yo voy a hablar de las cosas prácticas. Aquí es donde estamos ahora, estamos en el aula magna. En esta zona vamos a hacer las charlas plenarias. Acá afuera también va a ser siempre las pausas de café, y también la sesión de póster la vamos a hacer aquí afuera. Todas las otras actividades van a ser al otro lado, en los salones 6 a 9. Las charlas paralelas van a ser en los salones 6 y 7. Como somos gente muy precavida, tenemos el salón 8 en caso de que algo falle. Así que si algo se tiene que cambiar, va a ser al salón 8. Y tenemos disponible el salón 9, que es un salón que tiene mesas y sillas por si alguien en algún momento necesita trabajar en algo o conectarse. Es un espacio que va a haber disponible para trabajar o estar en un momento de silencio si es que socializar mucho los casos. Vamos, sobre todo hoy día, está contemplado el tiempo de cambiarse desde el aula magna hacia allá. Cualquier pasillo que vaya en esa dirección, el salón 6 y 7. En la página web también está el mapa y toda la gente que está acá le pueden preguntar cómo llegar. Sigan a la masa en el momento de las sesiones plenarias. Recuerden que este evento tiene un código de conducta que ustedes aceptaron en el momento de inscribirse. Básicamente queremos que este sea un espacio seguro para todas las personas, un espacio amable, es sentido común, vamos a tratarnos bien. Y si alguien tiene alguna situación que quiere reportar, puede escribir al correo de la TINR, ese es un correo que vemos solo nosotras tres, o se puede dirigir a cualquiera de nosotros acá de manera en vivo durante la conferencia, o nos pueden contactar por Slack. Y algo muy importante también, siempre que estén en las pausas del café o en el pasillo conversando, aplicamos la estrategia de Pac-Man, dejamos siempre abierto el círculo para que alguien se pueda sumar a la conversación. Así que no abren en círculos cerrados porque si no nadie puede sumarse y participar ahí. Y también, como una manera de respetarnos, si tienen dudas sobre la identidad de género de alguien, le pueden preguntar. Si tienen dudas sobre cómo se pronuncia el nombre o el apellido de alguien, le pueden preguntar. Esas son siempre preguntas bienvenidas para que toda la gente se sienta bien acá. La red es casi la misma de ayer, se ve parecida para quienes estuvieron en los tutoriales. Esta vez es LatinR todo con mayúscula. La contraseña es LatinR 2023, pero funciona solo en la zona de los salones. No hay aquí wifi porque queremos que estén bien concentrados mirando las charlas plenarias y no mirando el teléfono. Entonces esa va a ser la red y funciona en el lado de allá de la facultad. Recuerden que en el sitio web está el programa, que hay varias vistas del programa, pueden ver el programa resumido y también hay una sección donde pueden ver los resúmenes, los nombres y los contactos de las personas que van a presentar. Entonces la pestaña programa tienen varias vistas distintas para todos los gustos de cómo prefieran ver desplegada la información. En redes sociales vamos a estar ocupando LatinR 2023 como el hashtag para compartir las experiencias que están teniendo y amplificar el mensaje de las cosas que están pasando acá en la conferencia. Y recuerden que el viernes al final de la conferencia hay un sorteo, vamos a sortear la segunda edición del libro Art Packaging, que está autopublicada por Amazon. Hay que estar acá para llevarse la recompensa. Y el rumor dice que quienes participen en redes sociales, su nombre va a aparecer más veces en el sorteo y tienen más posibilidades de ganarse el libro. Y sáquense fotos con el cartel de LR Consortium, que es nuestro sponsor principal. Más todo en Twitter, LinkedIn, esas estamos revisando.
Y con un mensaje para Consorcio mejor.
Para agradecer a nuestro sponsor principal. Cuenta doble. Eso, ¿qué tenemos entonces para hoy? En unos minutos vamos a empezar con nuestra primera charla plenaria a cargo de Dai Cook. ¿Cómo sabemos lo que no sabemos? Luego en la mañana vamos a tener sesiones paralelas de charla. Los temas que van a cubrir estas sesiones son datos educativos, uso de datos para la toma de decisiones, aplicaciones de modelos y Shine en organismos públicos. Después está la pausa del almuerzo. Y en el bloque de la tarde vamos a tener sesión de charlas paralelas sobre comunidades y experiencias de enseñanza, datos espaciales, y después vamos a tener las sesiones de charlas relámpago, donde hay una variedad increíble de temas para enterarse de qué está haciendo la gente con R. Y en la tarde vamos a tener la charla keynote de Hannah Frick sobre Cognition Programming Edition, y esa va a ser en la tarde, después de la pausa del café. Y durante la pausa del café también en la escalera que está acá afuera vamos a tomar la foto de la comunidad de R-Ladies, así que mujeres y disidencias de género están invitadas a participar en la foto. Eso sería todo, así que bueno, muchas gracias por venir y damos inicio, por fin en Montevideo, a la sesión de LatinR.
Well, right now it's my pleasure to introduce Dianne Cook. First of all, I have to say that I am so happy to having her here. And she's a professor, a business analytic professor in Monash University. But I have the pleasure to meet her in Iowa State University, where she was working as a professor for more than 20 years. And I have the pleasure to be her PhD student there. And she is a role model for a lot of people right now, in the past, and probably in the future. Also is a role model for me. And what else we can say? That she is an expert in visualization, and today she will talk about how do we know what we don't know, and come on, if you are ready.
Can you hear me okay? Okay, great. First thing I want to say is thanks to Natalia, Riva, and Janina for organizing this. It's an amazing job and tough work. And all the other committee members it's just fantastic, thank you. And thank you all for coming. Giving a talk is a real privilege. It always scares me to bits, but it is a privilege to be able to talk and have your voice heard. So the topic, how do you know what we don't know, is like the eternal problem, right? That's what we're constantly seeking, particularly as academics. We want to know more. I can't promise that I can tell you everything, but I'm hoping that I give you some tools to know a little bit more about high dimensions than maybe before. So the focus today is on clustering in high dimensional data. It's something that we do on a regular basis. We organize everything into smaller groups, and it helps us make sense of the world. We start this at a very early age as one of our kids' activities is to give them blocks and ask them to sort them in one way or another way. So it's just something that comes naturally, but from an analysis point of view, it's one of the hardest things to do. And particularly it's hard because we don't know what the clusters really are. We're trying to discover them. And so having extra tools to help verify or give support for the final solution is beneficial. And this is where visualization plays a huge role. Visualization is one of the tools that allows us to see something unexpected and be surprised by what we see. And this is something that Chuki said a long time ago. The greatest value of slightly different from what he actually said, but the greatest value of a data plot is when it forces us to notice what we never expected to see. Okay, so these are the pieces that I'm going to discuss today. We're going to become familiar with the tour for viewing high dimensions. I'm going to show some method, the spin and brush method, and then describe more details of tours, and then related methods that probably most of us use on a regular basis, and then describe some particular aspects of clustering, connecting with cluster algorithms, model-based clustering, summarizing clusters, comparing methods, and comparison with dimension reduction methods. And also I'm going to leave some things with you that I hope it encourages more research in this area. There's a lot of open problems to work on, and there's a lot of interactivity in terms of R and other software that we really need. Okay, so as a theme, this relates to the parable of the blind men and the elephant, where each blind man touches one part of the elephant and describes the elephant in completely different ways. What we would like to do is to be able to look at the whole elephant and put all those little pieces together to try to understand the whole. So that's a theme, is to get some way towards being able to see the whole beast. So the methods that I'm focusing on are called tours. It's a pretty awful name now, but anyway, they're called tours, but basically it's just showing projections of high dimensions. So it's like playing the shadow puppets game, where, well, not quite, we play the shadow puppets game to show something that looks like something else with the shadow. But if you ask someone to rotate their hands, you'll notice it's not that bird, or it's not that dog or horse. But so essentially we're looking at high dimensions from the shadows, which are projections for high dimensions. And we also can take slices through the high dimensions as well to look inside the shape. So we have the tools to do those things today. So just for the mathematicians in the audience, it's good to put a little bit of mathematical notation behind what we are talking about when we're taking a projection. So if we think about a data matrix as having n rows and p variables, p columns. So we've got p variables. It's p-dimensional data. We can write the matrix out in this way. Then we think of the projection as a p by d matrix. So we're taking the p dimensions and projecting down into d dimensions. And typically that would be 2 dimensions. I'm mostly going to show just 2 dimensions today, but it can be 1 dimension or 3 dimensions, or even 4. So the D is flexible in terms of what low dimensional space we project down into. And so then our projected data we represent that as y. Okay, so here's your first tour, and d is equal to 1 in this case, and p is equal to 2. So you'll see that it's moving a little bit very slowly, and I've got a density being displayed, and then there's these lines being shown down here. That's being the changes in the projection matrix. So we're changing A11 and A21. So X1 here is A11 and X2 is A21. And so I'm just smoothly changing those values to give you a whole lot of one-dimensional projections of 2D. So I am curious to know, so notice that the changes, so the projection matrix is constrained to have values ranging from -1 to 1. So we're not changing scale of the data. And so you can see that here's some different values of that projection matrix, and you see the little axis there. So when we watch that 1D tour, what we can see are some bimodality. Is it still moving? Hang on, let me refresh. So we see some bimodality, only ever 2 lumps, and sometimes there's unimodality as well. So I want you to think about that, because this is what we'll need to do when we go to high dimensions than this. Just sketch on your desk or sketch in the air what you think that 2D data looks like, just based on the shadows. Everyone got a mental picture? Is this what you drew? Yeah. Okay, so the 2D data is just nicely 2 clusters, nicely round clusters. And what you were seeing in the 1D projections was like taking a line and rotating it around the data in some, and then on that line you project the data or squash the data down into that line. And so in some projections it's that bimodality, So if we look at it in this way, and we're squashing the lines points orthogonally into that line, you'll get the two very well separated humps. If you take this line, horizontal line here, and project the values, the dots into that line, you still get two bumps, but they're not as well separated, right? And then if you take this projection and project the points into this projection, everything is piled together. So it's just like a bell shape. Okay, that's the basis of the tour methods. And so from now we're going to be looking at two-dimensional projections. Here's a three-dimensional data set, and we're projecting into 2D. So you'll see the values, this is the representation of the projection matrix here. Now, because you have variables that contribute, all three variables can contribute in both the x direction and the y direction. So it's like those lines represent which direction the variables are contributing. Mostly, I've just selected a fairly small number, so it's x1 and x2, and then x3 gets introduced horizontally against x1, and then x1 gets introduced with x2 vertically. So it's just a small set of possible projections that are made. But what's the shape that you see? Well, we see some, I think we can put together as a 3D object because we're used to doing this. And it's a morning donut, right? Yes. But in the shadows we see some circular shapes. Because I'm using dots, I also get some transparency. So you can sort of see through the donut. In some projections you see that very, very important structure, the whole of the donut. But there's no clustering in this one, right? It's all continuous. All right, here's the next one. This is four-dimensional data. And again, I'm just using two-dimensional projections. And so you see the four axes here are just changing the values in the projection matrix to get that. So I want you to think about how many clusters you see. There's some disagreements. Yes. Okay, what are the choices? Okay, someone said 3. Any disagreement with that?
2 or 3.
Okay, 2 or 3. Well, 2 is clear, right? 2 is clear because one group completely separates from the other. Oh, but just that you just saw just now, I think. Okay, just occasionally you see 2 that are very close to one another, sort of slide opposite to one another. Yeah, so it is actually 3 clusters, but 2 are not separated. So, yeah, and also the shapes of the clusters, you see, I didn't ask you that, but every way that we look at it, it's either circular or elliptical for each one. So all 3 would be elliptical structures in 4 dimensions. Oh, yeah. Did you see an outlier? Let's see if I can see one. Now I need to know whether I can clear this. Wait, if I go to the next slide, I think I can clear it, but I've now forgotten how to, there we go. All right, well done, everyone. You can now tell your family and friends that you can see in 4D. Okay, so one first way of helping confirm or sort of remember the clusters is a method called spin and brush. It's been around for a long time, but it's been hard to do in R directly. So I'm going to risk doing some live demos here and see how this goes. Okay, so with spin and brush, you want to discover and mark. So when you see a cluster separate out, pause it and you highlight, you color that cluster, and then keep spinning. So I'm going to do this with the Detour package. It's fairly new. There's a Art Journal article that will appear in the next issue on it. So I'm going to jump out of the slides and go to my Studio window. It's where you don't need to see the code that's on the slide. If I go to the Detour code in here, here we go. I'm going to just run that code. Okay, good, that shows up. Are the points, I think the points are big enough to see from the back? Okay, I'll just zoom in and make this bigger. And so we have the same data, and I'm just running the tour again, but at any point, or I can pause it and come back. That's a good spot, actually. I can pause it and come back and choose to brush, and I think I can select all of these up here. And then I might like to change the color to make it a little bit prettier. Like that. And set them to be blue. Double click and then keep going. So that's the one we agreed on. Now the other two are a little bit tricky. But I could actually paint that outlier, right? So I could just paint this one. We'll mark that one as bright red. And keep going. Ooh. Okay, stop. Come back here. Wait, pause. All right, I can go back to that. Oh, no, I can't find it. Tell me when. Again. Just here. So that's pretty good. So I can paint a first part, but I also want to get some down here. It's a little bit hard to do. Let's change the color. Maybe we'll make it sort of a greeny color. And we can keep going because it's so hard to, I could select a few in here. But I feel I'm a bit nervous about that one. I'll just change it to a different spot. That's almost, you know. Well, at that point, I now have a mix in here that I think they're the same one. So let's grab the ones in here. Paint them. It's not too bad, right? But it's a little bit fiddly. If I kept going, I could probably get sort of slightly tighter set in that third group. But hopefully, with them coloured, now they can see it's arguable that there is that third cluster plus the outlier. All right, let's stop there and go back to slides. Okay, so a bit more about tours. And so the tour architecture it's very nice mathematics actually. But the basic pieces are you have your p-dimensional data, you have a projection dimension, and then you have, once you've decided on the projection dimension, you decide on how do you display it. If it's a one-dimensional projection, a histogram or a density plot, if it's two-dimensional, a scatter plot, if it's 3D, a 3D scatter plot, or if you have the choice, it's 4D, well, we get a bit of trouble, but we have some ways to do that. And then the second part of that is the algorithm that makes it all smooth and connects it together. And there's a lot of different choices in that algorithm. So there's two pieces of that algorithm. One of them is deciding which direction to move, which projection to show. And we were just looking at the guided tour, which is purely random. It's just choosing the next direction randomly, like a random walk. So that way we get to see the whole elephant. And the second approach would be to choose a new direction based on some criteria that we're really interested in finding. That's called a guided. And then the local would just choose randomly in the nearest neighborhood. So if I find a particularly interesting projection, I might want to just rocket back and forward close by to see what's nearby. And the last one that I use regularly is called a manual tour, where I can change the values of a single variable and rotate that variable into the projection or out of the projection. And the purpose of that is to decide, is this variable really important for that structure that we see, or it doesn't matter. But I'm just mostly going to demonstrate use the grand tour today. The other one is we have two interpolation methods. One of them is called geodesic, and that's the primary one. So geodesic interpolation is going to do that smooth motion through the space. And geodesic, because it's on a circle, to make sure that everything you see is orthogonal. Yeah. And then the last one, this is brand new, the Givens interpolation that allows you to go from the basis, specific basis defining the projection, to a specific basis. Purpose of the geodesic is that it within a projection, it's not allowing within plane spin, so it doesn't look like the whole object is moving around in that plane for you. All movement is out of that plane. So these types of tours, just small animations of each. The grand tour is what we were looking at with the 3 group data. The guided tour, you'll see that it's showing just the projections on the way to where we get a good single projection of sort of 3 clusters. And the slice tour is kind of nice. If you're looking at the torus, the slice tour is really pretty because it shows you all the pieces inside the torus. But here you would see that some points light up and some points fade out because it's slicing through the same data. Allows you to see inside. All right, I just want to make sure I'm not running too slow on time. So related methods, these are like the blind men with the elephant. They pick one thing and show that one. And this is what we want to get beyond. So principal components analysis of that same data gives you this view. These red lines are just the same as the tour axes. Right? So that particular projection from principal components analysis, it finds 2 clusters, but it would not allow you to easily see 3. And then if anybody's done nonlinear dimension reduction, the most popular ones these days, T-SNE and UMAP. There's about 6 or 7 different methods now that do nonlinear dimension reduction. But from a statistics perspective, we were doing multidimensional scaling, which was related to this for many years. So, but this is the view. It's a nonlinear two-dimensional projection. So nonlinear dimension reduction of the 4D data. It's the same data, and it suggests, you know, two very disconnected clusters. All right, so clustering with tours. I'm going to jump straight to model-based clustering, which is, I think it's very popular. It's very nice from a statistics perspective because it gives us a model underneath the clustering that we could then use later. So if you haven't used model-based clustering before, essentially it's taking elliptical shapes and trying to fit elliptical shapes to your data. All right, so same data, this is the penguins data, same data, and I am just using 2 variables, the bill length and the flipper length of the penguin. That particular set of 2 variables is pretty nice, actually. The clusters are, I didn't show this one before, and I've got the 3. Now I've got 3 clusters coloured based on the model-based clustering solution. But if I hadn't coloured them, you can sort of see just on their own that sort of like 3 higher density spots. Not real separation between those, between anything, but there seems to be 3 peaks in terms of density. So these 2 variables are actually pretty important in separating real species. But right now, I'm just showing the model-based clustering solution for those 2 variables, and the best one. So typically what we do with model-based clustering is fit the model to a number of clusters. So fit a 2-cluster model, a 3-cluster model, a 4-cluster model, 5-cluster model, 6-cluster model, 7, 8, 9 clusters. And then fit different shapes. So when it's just Gaussian, right? So you can play a lot with the shape of the ellipse based on the variance-covariance structure. So I fitted 4 different shape models here. EEE is elliptical, but all the same ellipses for the clusters. So if I fit 2-cluster model, it's allowed to fit 2 clusters with 2 of the same shape ellipse. Yeah. All right, so those are just the different shapes. And then if we look at BIC as the criterion for which models are best, this lightish yellow one up here, which is the EVE, and I can never remember what EV, all of the code means. I had a little link in here to go back to the model to find out which one that was. But I think we can sort of work it out from here. It's elliptical, which means there's some covariance, but it's allowing some variability in the size of the cluster. I think they're all the same direction, but I think the size of the cluster changes. Anyway, so that's what I've shown on the right-hand side. This is of all the number of clusters, they all agree, regardless of variance covariance, that the 3-cluster solution is the best. Yay. It's what we sort of picked out from viewing it. And this variance covariance model is the best. So that's what's being shown here. The points are coloured according to their cluster identity, the cluster label as given by that model. And these elliptical points here I added to the data to show what the model estimate is. Right. So that's the estimated model. Right, so let's do this in 4 dimensions. So this is the BIC plot for 4 dimensions, for the full data. And I'm fitting the same number 2 to 9 clusters and the same 4 variance covariance models. And just on BIC alone, it would say that there's 4 clusters is the best model. But most, there's also this, most of the models are pretty similar at 3 clusters. Right? So they're sort of all agreeing there that there's 3, whereas the different variance covariance breakdowns would disagree on the 4 clusters. Right? Okay, so let's take a look at their solution. So this is the 4 cluster solution. Okay. So that's the 4 cluster solution. What did it do? It took that really big separated cluster. I mean, it's that one big cluster that was pretty cohesive, pretty elliptical, that we all agreed that that's a cluster, and it chopped it in 2. That's interesting. Yeah. Okay, so the question, if I go to the best 3 cluster solution, so all the different variance covariance models sort of agreed with BIC value. So in that case, you pick the simplest of those variance covariance models, which is the EEE. And that's the EEE model. So I've got points added on here, which are the ellipse corresponding to the variance covariance matrix on top of the data. They're slightly different, slightly darker shapes. You can see that, right, that the difference between the ellipse and the data set. Which of those 2 models do you think is the best one? The 3 cluster one? Yeah, I think, I hope you agree that the 3 cluster one visually fits the data better. And that's the goal here, right? So if we rely just on the BIC values, you know, it's a nice sort of fixed, reliable method, but whether it really actually matches the data, it can still be tricked by little complications in the data. All right, so next one. Next example is summarizing clusters. Often what we do in 2 dimensions is when you've got a cluster solution, you wrap a convex hull around the outside of it. And so if I just look at the 2 variables and show the convex hull for the cluster solution, this is Ward's linkage hierarchical clustering in this case. Just trying different clustering methods for the heck of it to give you some different examples that it works with different cluster algorithms. But anyway, this is Ward's linkage hierarchical clustering on 2 variables. And with convex hulls around it, well, we can do convex hulls in 4D. It's messy, but we can do it. The convex hull algorithm runs in R for any number of variables that you give it. So here's what it looks like. It's just a big polygon. So there's a lot of lines in there, but if you think about each view that you look at, each projection that you see, that's the same as this. The outside lines would be the convex hull. So what do we learn from that? This clustering solution has done a really nice job of picking that cluster that's well separated out. And it's not done too badly in terms of the 2 that are really close to one another as well. If you look at the convex hull, you see they overlap a bit, but in some projections, they don't overlap very much. Yeah. All right, so we can summarize with convex hulls in 4D too. Yeah. All right, next one. I'm going to brave a live demo again. I've got 2 different clustering methods. So this is often what you do when you're doing clustering because we don't know a truth. We're going to throw a bunch of different clustering algorithms at it, get some results back and decide which is the best result. Right? So, or decide where they agree or disagree. So I've got Ward's linkage clustering with 3 clusters, and I've got model-based clustering with 3 clusters. And this is the confusion table. There's 149 observations here where both methods agree they're the same. And we have 119 observations here where they both agree that they're the same cluster, that they're in the same cluster. And I've got 57 observations here. So for the most part, Board's linkage and model-based agree. There's only 8 observations where they disagree. So it would be interesting to see which 8 observations that they disagree on, right? So that's what we're going to do here. I've got this in 2 different ways. So this is using detour again. Oh, my colors have, sorry, I did have colors, they're matching, it's all right, but they're the different colors from what's in the, I thought I could zoom a little bit. I can't zoom. But what we've got on the right-hand side here is the confusion matrix. So these are the big blobs are where the 2 methods agree. And then these are the 8 where they disagree. Let's run the tour. Actually, I'm going to switch to the alternative because I'm going to show this for dimension reduction as well. So let's run the tour on the right-hand side here. So as you look at the tour view, so this is what I've colored by is the Ward's linkage clustering. And what I'm interested to know, so this is the Ward's linkage clustering. What I'm interested to know is where these 8 points land. And I think if you look at the red and the blue cluster, I can turn them on. If we just focus on those 2, there's a few points that are a little bit scattered, few of the blue points are a little bit scattered in amongst the red ones. Those are the ones where there's confusion. Let's see if I can grab. If we no, that doesn't work. This is a little bit hard, but it's these 8 points, if I stop it, it's the ones that just, the sprinkling of points that are further away from the blue group, confused with the red group, is where the difference between the 2 cluster solutions are. Let me just stop that and go back to the next example. So I showed you the nonlinear dimension reduction before, and the T-SNE view had two clear clusters. I want to show you what this actually looks like. So the software here is liminal, again. Okay, so using the same software here, I can link the tour in the right-hand side view with the t-SNE view on the left-hand side. And so what's happened here, the coloring is actually the true clusters in this data, the species cluster. And you see what's happened with t-SNE? That's often the case with nonlinear dimension reduction, that it gets quite confused about things. So it's actually taken one of the groups and split off a small clump. So what happens if I just focus on that yellow group, which t-SNE says that yellow group splits into two, and look at that yellow group on its own? Do you agree with what t-SNE did? Makes no sense, right? Okay, so this is why we need to have some ways to examine the solution when you're doing non-linear dimension reduction, because it does weird things to data. It always looks great, but it may not be reliable. All right, I'm running out of time with all my flaky demos, but I just want to say, to finish off, the things that we can't do yet. So the tour package provides the infrastructure for generating those paths, and it's really pretty good and really sound. What the detour package does is it just builds on that. It generates the path in R and drops it out to JavaScript. And you'll see that I actually only had a fixed set of projections to look at, but it's probably enough. But it gave me really fine-tuned control of brushing between things or highlighting things and some interactivity. But there's still a lot of scope for more interactivity, which would just make using the tour much easier and more applicable to various problems. And then lastly, integration better with lots of our different algorithms. Particularly that's important for more supervised classification methods where we have a lot of diagnostics and we want to be able to connect better for those, but particularly in terms of understanding complex models and explaining them. So this is fun. Some of these methods are in a new book that we just put together. So thanks for listening.
Was really nice. Do you have any question for Dai? You can make the question in Spanish. Sí.
What do you think is the role of VR or AR in this kind of tours of data?
Yes, so virtual reality gives you the third dimension, and it can be useful. So I haven't done much in virtual environments for a long time, but in the 1990s when VR was sort of emerging, I did do a tour in a 3D virtual environment as a just experiment. And we also conducted an experiment to see whether people could see more with 3D projections as opposed to 2. And for clustering, yeah, it helped a bit. It didn't help enough for me to warrant the time taken to go to a special computer, a special display. But you can see slightly more in a 3D setting. The interesting thing is, though, that 3D is still based on 2D. Yeah, so, which is one of the reasons why focusing on 2D is sort of the mainstay. Yeah, thanks.
Any other question? ¿Otra pregunta? Caray.
Thank you for the talk. I'm a biologist, and I was looking at this clustering with the species, and I was thinking that maybe these other types of methods that showed like the fourth cluster or something could be like raising a hypothesis that there's some speciation going on or another. Do you know any work that uses this in this context to?
It's so tough question because I don't know enough about. This is sort of weird. So speciation's a tough problem, I think, in terms of you looking at evolution of the species. So in theory, yes, because you can look at the variables that are describing your clusters at epoch 1 and epoch 10, and you have some persistence of the species ID, or some ID of the individual, so you could map the individuals back, or even if you don't, you could still have separate entities clustered, and some comparison whether the clusters are similar or not. So I think there's scope for it. I don't know of anyone doing that, so that's a good future research topic. There are some similar things that I've done. So if you think about hierarchical clustering, we have dendrograms. And the difficult decision is, where do you cut that dendrogram? And so we have used this same linking between plots to show the dendrogram in one view, and you've got all the individuals sort of piping through that dendrogram. And if you select a node of that dendrogram and then watch where it is in the tour, it helps decide whether that cluster should be a different cluster, or that group should be split into two clusters, or it's too cohesive to really think about it. So main thing is it should be easy, it should be possible, but I don't know of anyone who's worked specifically on that problem, and I'd be interested. Yeah.
Una pregunta más, pregunta.
Nice to meet you. My name is Mateo, and thank you for coming to the presentation. This question is not related to this presentation, it's related to R. I will say, how do you learn R, and when do you know that you know R? Because I would say I'm pretty a freshman in R. I'm learning to coding, and this is actually my first presentation here at the university, so I know it.
Max, Hannah,
Thank you.
I think honestly, you never really know enough. I think that's a paradox of education, in a sense. The more you learn, the more you realize, I don't know enough. But I would think, to me, is when you can do a data analysis, that's when you know enough. And that's, I think, one of the main beauties of R. It's not the language in itself, it's what you can do with it. And it's a language of data analysis. And even if it's not as efficient as Python, it really helps you to think clearly through a data analysis, particularly if you follow the tidy R for Data Science book. That's the most brilliant step your way through learning data analysis skills. That's when you can be just super powerful, right? Things went around when I was doing my undergrad. The computers were all in these gigantic big silos, and you put cards in the computer, and I thought computers were pretty dumb. And I didn't want to learn it, but I had to as a requirement for class, and I have to say I cheated because I had to write 5 programs to do stupid things. So I just borrowed the cards from someone else and plugged it into the thing, and I passed. But I've come a long way from those days, and I've really learnt how to work with R and a few other languages before that, and I feel like I am so powerful these days because I can take data when it's made publicly available and I can say what they're saying in the media, it's bullshit, right? And particularly the bushfires in Australia 3 years ago, and we're likely to have bad bushfires again this year. There's a lot of public data around and a lot of new data on satellite hotspots. The media was just rife with saying there's a lot of arsonists running around. I thought, I sort of feel like that must be true. People are horrible. But actually, if you pull the data together, absolutely not. The problem is lightning. The problem is storms. And those fires are starting in remote places in our pristine forests, which should not be burned. And it's clear just by, so that's a sort of thing that I can do when you know enough in terms of data analysis. Same with when COVID started, I started pulling data down for myself to think, okay, how much do I need to bunker myself in my house? Well, yes, but not really for me, it's for other people because the spread is the worst issue rather than your individual risk. Yeah. So, yeah, enough to be a data analyst.
Muchas gracias, Dai. Bueno, robé el micrófono, los invito yo. Robé el micrófono, vamos a la pausa café que va a ser bajando la escalera. ¿El qué? Hay un canal de YouTube de Latiner donde va a quedar la conferencia de Dai y todas las conferencias magistrales. ¿Vale? Gracias.
Oh my God,